Alright, so the roots of complex numbers, we have already looked at square roots. Okay, so we looked at technique to how to find the square roots of a complex number. Okay, by simplifying quadratic to have complex roots. For example, okay, so this is another method that we can use. Alright, so in our notes, we've got the formula there. Okay, so it's really coming from saying if z equals, so z to the n is x plus y I. Okay, which equals our modulus times cis of the argument. Then z, so we're finding the roots, so we've got the power of n for some complex number z, and we're finding the roots for them. Okay, so it becomes r cis theta to the 1 over n. So like taking the square root, if it was 2, we'll take the square root of that side. If this is cubed, we'll be taking the cube root. So we're taking the nth root of that. Okay, and we get that little expression there using De Moivre's theorem. Okay, so I'm doing a bit of manipulation as well. Okay, so r becomes to the power of the root power of n times cis, and then doing a bit of manipulation. Okay, we're going to get this result here, the 2 pi k plus your argument or over the value for n. Alright, and this will work when k is 0, so that's when it starts. That's the other part of the manipulation. We'll start when k is 0, not 1, and we'll go all the way up to the value of n take away 1. Okay, so if this n was 2, we'd be only looking at 0, k equals 0, and k equals 1. Alright, so if n was 3, 0, 1, 2. Alright, so we look up to the n, take away 1 for the values for k. Alright, what does this mean? Alright, so there's our couple of examples. Then we're finding the square root of the complex number 9i. Alright, so before we look at the root, we need to first consider the modulus and the argument. So z, modulus of z, is going to be 0 squared, the square root of 0 squared plus 9 squared. Okay, so the modulus is just going to be 9. And of course, because that's the point on your imaginary axis with the distance 9. Okay. What's the argument for an angle of a complex number on the imaginary axis? Positive. Alright, where is 9i? On there, isn't it? Okay, what is the argument? Yep, so it's pi on 2. Okay, so in other words, theta is tan inverse of y over x. Okay, so it's going to be 9 over 0. Okay, and of course we can't divide by 0. So the value for tan that we don't have a solution is pi on 2. And multiples of pi on 2. So if we put tan of 90 in there, we won't have a solution. Okay, we'll actually have asymptote at that point, and we'll look at that further when we get up to the topic in mathematics. Okay, so in other words, theta is pi on 2 because I know it's in the positive imaginary axis, so I know it's a rotation of 90 degrees, which is pi on 2. Okay, so I've found my modulus and argument. I'm going to put it into this formula here. Alright, so z is going to be n is 2 from the power. Alright, so it's going to be the square root of 9 cis of 2 pi k plus the argument pi over 2 or over the value of n, which is your power. Alright, and this formula will work when k is 0 and 1. Okay, we've got two solutions, so we've got up to n take away 1 to 2 take away 1. And we're finding the square root, we're finding two solutions. Okay, so all we need to do now is substitute the value for k in here and tidy up that expression. Alright, so k equals 0. Z is going to be the square root of 9, which is 3. Cis. Alright, so 0 goes here, so that will eliminate that part of it. We've got pi on 2, all over 2. So we've got cis of pi on 4. Okay, so we can go back and represent that as our complex number. So back from polar form to complex number form. But I'm just illustrating how to find it, and I'm sure you guys know or can work out now how to convert that back to complex number form with the real imaginary part. So k is 1. So the square root of 9 is 3. Cis. So 1, we've got 2 pi plus pi on 2. So we've got 2 plus half, which is 5 over 2. 2 and a half, which is 5 over 2, all over 2. Okay, so it consists of 5 pi on 4. Okay, what is the degree of pi on 4? Pi on 2 is 90. 45. What's the degree of 5 pi on 4? Pardon? 225, your head? Yes? Right, what do you notice about those two angles? They're the same. They're sort of diagonally opposite, okay? So, your roots will form a sort of like a circle sort of thing, okay, because the modulus is the same. So, in 45 degrees, we've got our first root, so I'm going to call it Z 0, big when K 0. Okay, so I could really say Z0, Z1. Alright, and then 3 cis of 5 pi on 4. Okay, so out there, and we actually form the circle. Okay? So that's one thing we're doing when we find our roots, okay? We're actually plotting them around in a circular form. Okay, any questions on that? Okay, so that's the more straightforward one. We need to now find the fourth roots. Okay? So when you see fourth roots, it means the expression is going to be z to the power of 4 equals that. Okay, fourth roots, z to the power of 4 equals negative 8 plus 8 root 3 I. Alright, so what we're really finding z for is equal to 8, negative 8 plus 8 root 3i. So we're finding the fourth roots, okay? It means we're finding 4 roots around the circle that formed by that complex number. Okay, so the first thing you need to do is always find the modulus, find the argument, okay? Just for z, okay? Square root of x squared plus y squared, 64 plus 192, when you work it out, and that will give us a sum of 256, and nicely it gives us square root of 256, which is 16. Alright, so the argument, tan inverse of the imaginary part, 8 root 3 over the real part. Alright, and now we need to consider the quadrant to get our actual angle. Alright, so we can cancel the 8 and the 8. So it's a tan inverse of negative root 3. Which quadrant is my complex number in? So negative, then positive for your real and imaginary part. So somewhere in the second quadrant. Okay, so what's the basic angle? Tan inverse of negative 3, tan inverse of root 3. So the basic angle in radian measure is degree measure is 60 degrees. So in radian measure is pi on 3, and we represent an angle in the second quadrant by 180. Take away the basic angle, so So theta is going to be pi for 180, take away pi on 3, which is 2 pi on 3. So we've seen this one before today as well. Okay, so the formula you need to remember, otherwise you're going to have to derive it. Okay, Z equals, so the formula back on the other page, the nth root of the modulus, so we have the power as 4, so it's going to be the fourth root of 16. Cis of 2 pi k plus the argument, so 2 pi and 3, and everything is going to be divided by 4. Okay, so it's going to be the fourth root of 16, cis of 2 pi k plus the argument, which we just calculated, or over n, and n comes from the power or the number of roots you need to find, which is 4. Right, and this will work when k equals 0, 1, 2, and 3, all the way up to n take away 1. So 4 take away 1, we're finding 4 solution. Okay, so what's the fourth root of 16? 2. Okay, because 2 to the power of 4 is 16. Okay, so we're going to be forming a circle of radius 2, and we're going to find that 4 solution are going to be evenly spaced out around the circle. Okay, what's going to be the separation between two complex numbers, between the two roots, sorry? Yep, a right angle. Okay, because we're evenly spaced around the circle, it means each of the points is going to be formed at a right angle. And the starting point is dependent on where the complex number starts. Okay, so k is 0, so z 0, so we could really say z to the k. If we want, is equal to 2 cis, so 2 pi k, k is 0, we get 2 pi on 3, 4 over 4. Okay, so 2 pi on 12, so pi on 6. So that's where the first one is, and then each successive one after that will be a separation of 90 degrees, or in other words, we multiply by okay. When we want to have a rotation anti-clockwise by 90 degrees, what do I multiply by? I. So really I can go from here and can multiply each result by I from the previous line. Okay? Or I just keep going with this. K is 1, so Z1 is going to be 2, so the modulus is going to be the same. Okay, so remember you are dividing really 4 times when we're finding the root. Alright, so we're going to keep dividing the argument and then do a subtraction of the argument. Alright, 2 cis, right, 2 pi times 1, which is 2 pi, so 2 pi plus 2 over 3. So it'll be 6 pi on 3 plus 2 pi on 3, so 8 pi on 3, all over 4. So 8 pi over 12, which simplifies to 4 pi on 3. Because I know pi on 6 is 30, pi on 3 is 60, 60 times 4, hang on, that's not right. We've done 2 pi plus 2 over 3, it becomes 6 over 3, 8 over 3, 12, 8 over 12, that's 2 pi. On 3. 8 pi on 12 is 2 pi on 3. Okay, so pi on 3 is 60 degrees. 60 times 2 is 120. Okay, so this is 30 degrees and this is 120 degrees. Okay, so we are evenly spaced around the circle for the value for n. So we have 4 roots, we have an evenly spaced of 360 take away divided by 4. If we had 6 roots, it'll be 360 divided by 6, and there'll be a separation of pi on 3, 60 degrees, around your roots. Okay, so that's why I knew there was 4 pi on 3 is not correct, because I know there's a separation of 90 degrees, rotation anti-clockwise, for your complex solution, for your roots. So, K is 2. So, Z2 is going to be 2. So, I know that 120 plus 90 is going to be 210. Okay, so that's my check when I do the answer. So, we've got 4 pi plus 2 pi on 3. So, K is 2, so we've got 4 pi. So, we've got 12 pi on 3 plus 2 pi on 3. So, 14 pi on 3 all over 4. 14 pi on 12. 7 pi on 6. The pi on 6 is 30. 30 times 7 is 210. Alright, so you can do it that way if you've got that theory. Okay, so all you really need to do is work out your first solution and then rotate when you work out the value, the separation of the angles between each of those, as opposed to doing this. Alright, K3, so I know it's going to be 210 plus the 90, so I'm going to have 300 degrees. Okay, so Z3 is going to be 2 cis. So I'm really adding pi on 2 each time, aren't I? For your angles. So 7 pi on 6 plus pi on 2 becomes 10 pi over 6. Because pi on 6 is 30 degrees, times 10 we get out 300. Okay, and I'm adding another pi on 2. Sorry. Nope. Definitely bits. When you do that, you just get back to the start. Okay, for Z0. Okay, that's why we stop. Okay, so really, alright, so we have, I've shown you how to go from a polar form back to a complex number form with the real and imaginary part. Okay, by evaluating the angle in each of the quadrant. Right, so what we're saying is that the modulus is 2 and the first one's at 30 degrees or pi on 6. Okay, so the roots, so 30 here, so Z0, and then the next one was 120 or 2 pi on 3, Z1, another 90, Z2, and another 90 or another pi on 2 around anti-clockwise, or we can just work out the first solution here and multiply everything by I, because when we multiply by I, it gives us a rotation of 90 degrees in an anti-clockwise direction. Okay, so that's your technique and that's your skill to look out for when you're working through these questions. Right, any questions on that?